Okay guys, we are going to start with the second half of Unit 1, okay? And we're going to start with continuity. And continuity visually is a lot easier to understand than these proofs. So what we're going to do is we're going to visually look at what do each of these pieces of this proof show visually. Okay, so the number one rule with continuity is that, first of all, a function f is said to be continuous at x is equal to c. Okay, so c, right off the bat, I want you to understand, it is an x value. It's on the x-axis somewhere. Why do you think they use c?
It's a constant.
It's a constant. So c for a constant, yes, it could be a negative number, it could be a fraction, it could be some kind of constant. But it's an x value, okay? So imagine that on the x-axis, okay? So rule number one is f of c is defined. That means it exists, okay? So you see it somewhere on the graph. There's not a hole in the graph like a removable discontinuity. There's not a vertical asymptote like an infinite discontinuity, stuff like that. You know what I mean? It's defined. It's in the domain. Okay, and if you want to write that, you could say that the domain spits out a y value. Okay. Number two, the limit exists generally as you approach c. So the limit as x approaches this constant on the f of x graph exists. Okay? Go with me? Okay. And then the last part is rule 2 is equal to rule 1. Okay? So I'm going to jump a little bit ahead because I like to show this early, okay? So first of all, let me show an example of where f of c is defined. Let's say that this is c. And if f of c is defined, that means at c, anywhere, there is a point, and it is closed. And we call it f of c. Okay? That's this part right here. Let's show now that the limit exists. So we could show that this limit could be like way down here. And right here, whatever that y value is, would be the limit of what it equals to right here. So it'll show of what it exists. And you know that because you just took a test over limits just now. Now the question that you have to ask yourself is, are these two values the same? This value here in 1 is this y value right here. This value here in 2 is this y value right here. Guys, do those look visually the same? No. So that's why it's not continuous. Imagine that this is a roller coaster, let's say at Six Flags. Would you want to get on that roller coaster? No, because there's a big old gap. It's missing some tracks. It's not a continuous roller coaster. You with me? So our goal is to make this continuous. That means this piece right here, this y value, needs to equal whatever the other y value is. Okay, so just keep that in mind. Alright, so here we go. Let's go ahead and keep going. And our first one says, sketch a function f so that f of c is not defined. Okay, so imagine an f of x. And at c, it's not defined. Anyone, what could that look like?
Anything with a discontinuity of any kind.
Like what? What do you specifically? Let's do two variations.
Two graphs going towards infinity.
Okay, so two graphs going to like this. Perfect. And c could be right here at x is equal to 0. What else? What's another one that we've done? Removable discontinuity. You could have one that looks like this, where this is c. F of c is not defined. Okay? Now b says the limit of f of x does not exist as you approach c. So now if the limit doesn't exist, let's do two graphs. Okay? Jordy, what would this look like? What's one variation where the limit does not exist?
Like you could do
Okay, perfect. So now let's do one where, let's say C is over here, and this one goes down, and this one goes up. The limit does not exist. Perfect. Arjun, what's another one that we can do?
Two one-sided jumps.
A jump discontinuity? So you're saying like, here's C, like we were doing some of those that look like this? Okay, perfect. There's another example of a function, the limit does not exist. Okay. Nate, we're going to look at C. It says f of C is defined. And the limit exists, but the limit is not equal to f of C. Nate, what could we do? What could we draw that would satisfy those conditions? Someone help him out.
Point discontinuity.
Point
Jump discontinuity. Like, well, if you it goes like straight line, right?
straight line with a hole in
and
it.
then a point on top of it.
Perfect. Okay, so here we go. So here's a graph showing that a limit exists at C. And at C, we're going to show a point up here. So it's like a removable discontinuity, but the point is way up here. Do y'all see that? So that is a perfect example of this for sure. Can y'all think of another one? Another example variation?
If you had a jump discontinuity, but one of them was built in.
So a jump discontinuity, does the limit exist? No, it's okay. These are good questions. These are good questions, and they're good mistakes to make because you're asking yourself the pieces of the proof. You know what I mean? So we can't do this, and I know what you were thinking of, like this graph here, but have one of them maybe filled in. But we can't do that. Is there another way that we could do this? Matthew, do you have a suggestion of how you could draw this? Okay. How about this one? This one's a little weird. This one's... You could have something like that, right? I know that would never happen, but technically it could. I mean, the limit exists and f of c is not equal to that limit. You with me? Let's go to D. It says f is continuous at x is equal to c. Here we go. This is what we're trying to develop. Rule 1. At C, it has a y value. It's called f of c. And in blue, so this right here that we just did, guys, is rule 1. F of c is defined. Notice the word defined for functions, whereas with limits, it's does it exist. So as x approaches c, we want it to exist. Okay? Let's do this in blue. So number 2 we'll do in blue. We could say that it looks like this. And then number 3, where rule 2 is equal to rule 1. And the attention to detail is about to skyrocket, okay? As far as what you're going to show today, what you're going to show for the rest of this unit, as far as it can't, you'll see whenever we do it examples, it has to be in this form pretty much exactly. Okay, so visually, here we go. F of c is defined. Here's the y value. The limit exists. It's right here. And the fact that they're equal to the same shows that it's a continuous. It's continuous at c. Cool? Okay. Here we go. So let's do a point discontinuity, a jump discontinuity, and an asymptotic discontinuity. So real quick, we'll do one example of each. And just real quick, to make sure that you're solidified, let's say this is C, and this is C. And we want to show where it's not continuous. A point discontinuity will look like this. A jump discontinuity can look like this, and one can be shaded in, or both. And then an asymptotic, we've already kind of looked at this, would be something that could look like this. Alright, so a point discontinuity is said to be removable. This is why we call it a removable, because the function can be redefined at the point in such a way as to make the function continuous everywhere. So basically, this point right here, if I were to redefine it, okay, and if I were to actually move that point, so if I were to actually move that point up, then the function is continuous. See, but if I did that over here, it would not make it continuous still if I were to move it. And then over here, despite wherever I move it, it won't make it continuous. That's why this is a removable, and these two are non-removable. You with me? Okay, only one point separates this right here from making that ET moment that I was talking to you guys about before. Whereas no matter what, you're not going to get an ET moment here, despite wherever you slide that point. Okay. A function f is continuous at a left endpoint or a right endpoint. And there was a phenomenal question that I had earlier on today during second period. Let's see if you can find the same question. I think you can. This right here is basically rule 3 of continuity. But it's only looking at what? One-sidedness, right? It's saying approach A from the left. See, this one's saying approach B from the right. But it's the third rule of continuity. So my question to you is, can you be continuous one-sided, or do you have to be continuous only two-sided? You can be continuous one-sided. You can. You with me? So this is saying, watch. Again, the graphs help tremendously. Let's say this first one here, we're going to approach A from the left. So let's say A is right here. For the limit to exist, that means it has to be going to something quantifiable, and it can be an open dot. And for f of A to be defined and equal to, that means this must be closed in. So it looks like basically this graph that's stopped. Are you all with me?
So that is continuous.
This is continuous. Could I draw this that you see in blue without lifting up my pencil?
Yes.
Yeah. And then now if I approached B, let's say B is here, and I approached it from the right, whatever it looked like, and I stopped, and I put a point, defined point because of that, is that continuous? Yeah, it's continuous from the right. So is there a question that you have right now?
What if it's not a function?
Okay, so not a function, yes, you obviously it wouldn't be, and I drew that very badly for you to ask that question, but that's not the question I was looking for. No, like what I'm saying is that you can be continuous one-sided. You can be continuous one-sided. You can also be continuous general limit-wise, both-sidedness. My question is this. Let's say this is A, and I'm doing this right here. I'm approaching A from the left. Is that continuous? So I have both answers. It looks continuous because I was able to what? Draw it without picking up my pencil. But the definition of the derivative, the very first rule says that A must have a y value. Go with me? And it doesn't. So it's not continuous at A from the left. Does that make sense, guys? What's another way that you could have shown that? Oh, wait. Obviously now, is it continuous? Yep, because f of a exists, it's defined, the limit exists, and the limit is equal to that point. You with me? So, what's another way that I could show this? Let me ask you this. Yes, yes. So here's A. Let's say that I have this approaching a vertical asymptote. And there's, you see, it's all about this right here. If I approach A, but never actually hit it, is this graph continuous from the left? No. Because you have to hit a quantifiable defined y-value point. And infinity is not quantifiable. Go with me? Okay. So, now that we have that out of the way, we're going to go for points. Okay? What I want you to do, let's do these first two together. Please don't work ahead, okay? Please don't work ahead. We're going to do the first two together and then I'll let you do the rest. We're going to find the x values where it's discontinuous. We're going to identify the value as a point, jump, or asymptotic. And then we're going to identify is it removable or non-removable, and then we're going to sketch the graph. So actually, I'm going to pause the time, and I will give you to do both of these 4 minutes. You might have to divide and conquer amongst your groups, but I'll give you 4 minutes to work it out, and the solutions will be up here when we're done. All right, so going to what this would look like. Oh yeah, don't look at that. Oh. I think this one's it, right? Okay. All right, so the first one. Yeah, this one. If we factored out, just like we did in the first part of Unit 1, and we canceled out x equals 2, we know that the discontinuity occurs at x is equal to 2. So there's a hole in the graph, and everything else that's left over, in this case this x plus 2, is going to be graphed, and that's what you see as far as right here. But there's a hole in the graph. It is a point discontinuity, it is removable, and there's the graph. Okay? Over here, this is just 1 over x shifted 3 to the right, and you see the discontinuity occurs at 3. It is asymptotic, it is non-removable, and there's the graph. So 1, 2, 3, 4, 5, 6, 7, 8. And if you got it perfect, I'll give you 160 points. Okay? So real quick. Team 2. Whoops. Alright, so the next points that I want you to observe are going to be these two. Graph what they look like. Actually, no. All 4. That's why this one's a huge one. So we're going to have all 4 graphs and all 4 parts for each of those graphs. So there's 16 right there. There's a lot. And there's a little bit more than 16. Okay? I'm going to give you time to divide and conquer or work in groups. But because there's 4, I'm going to give you 6 minutes. Because there is going to be a little bit divide and conquer. No, I'll give you 7 minutes. I'll give you 7 minutes to talk about this all together, okay? Go for it. Okay, so the question that I just had was this. What if we have a function that looks like this, and this is c, and I asked, is it continuous, is f of x continuous at c? You have no idea how huge this question is, though. Yes or no? Is it continuous at c? No. Which of the 3 rules did it fail?
The first one.
The first one. So as soon as, remember, all 3 have to be true to even stand a chance of being continuous. If any one of these 3 are not true, then you could just say, because of this right here, theorem doesn't hold. Therefore, just 3 dots, f of x is not continuous, and I know it's subtle, but it's huge and important. It's all about derivatives at x equals c. Okay, the question was this. What if instead of c we had -3? Guys, what is this value right here? Right here? What would I label this right here? Not f of x. F of -3. Okay? And that's a big oh moment because it helps you solidify your 3 rules of continuity and you're making sense of it. This is a really good question because rule 1 says, does f of -3, is it defined? Yeah, you see it. It's right here. It's on that line. Does the limit of f of x exist as you approach -3? Yes, it does exist. It's whatever that value is. And does rule 2 equal rule 1? Yes. So here's the thing. You would say, therefore, f of x is what? Continuous. Big O huge word. I know it's so subtle, but guys, you're going to learn this word is huge. At what? X equals -3. So, in general, this huge function, is it continuous everywhere? The answer is no. But is it continuous at 3? Yes. Is it continuous at 0? Yes. You with me? So you can be very descriptive of where you're continuous at. Okay, so now let's go ahead and go to our answers. Okay, so the answers that we have now are the following. And let me show you how I want you to highlight the pieces. Okay? Alright, so we have the graph at x is equal to 3. It is jump. It is non-removable. The graph at x is equal to 1. It is jump. It is non-removable. Before I continue, this right here is super, super important to make this unit so easy. Do any of these piecewise function domains have equals to 1? Yes or no? No. But I'm going to ask myself, what if? What if x equaled 1 on the first one? Well, I would have 1, 3. You with me? What if x equaled 1 on the second one? What would I have? I'd have 1, 1. I know they're open because of these domains not being equal to. So it helps me in 2 ways. One, a better graph. And I can see, are they touching or they are jump discontinuity because of my what if moment. And the harder questions that are coming, the what if moment will make it so much easier. You know exactly where to start from. So what if? Okay? Do you understand what I'm saying by this? Okay. Let's come over here. X squared, this was not a trick question, just wanted to make sure people were good. None, none, and none, because it's continuous everywhere, and that's what the graph looks like. Over here, there's 2. So if we factor this piece out and we canceled and removed it, this is the hole in the graph. That is at x is equal to 0, which you see right there, with the y-axis. Okay? And then x is equal to 3 is your other one, and that's, so you have 1, 2. The first one's asymptotic, the second one's point. The first one's non-removable, and the second one is removable. And then you have 2 pieces to the graph. I want you to have shown the vertical asymptote and also to have shown the removable discontinuity. So let's count how many we have. We have 4, 8, 12. And then we have 1, 2, 3, 4, 5, 6, 7, 8 here. 4, 4, and 4. So 16, 20. Out of those 20, team 2, whoops. How many did y'all get? So now let's keep going.
I'm still kind of confused.
On what part?
For F.
Which one? This one here?
Yeah.
Okay.
You go back to the.
Yep. For F, go ahead.
Because we got the discontinuity at the y equals 0 on the y-axis, but how is the discontinuity not at x equals 0?
What is that x?
It is at x is equal to 0. That's what I have right here. I have at x is equal to 3 and 0.
But it never crosses the x-axis either.
It has to have a point on the x-axis.
Let me understand his question. He's saying, does it have to cross the x-axis to be discontinuous? It doesn't have to. It could be anywhere, right? It could be a graph that looks like this. So let's say that this is shown here. Christian, real quick.
Yes.
Is this discontinuous at C? Yes. So this is kind of close to what we were just looking at. Even if this openness was here, is it discontinuous at C? So we're saying this is discontinuous at x is equal to 0.
Oh, okay.
Okay? Cool. All right. So let's go now to this piece. Now I'm going to model this first one with you. But the second one, I want you to see as far as how you can build it. Okay? So here, let's do this first one together. And then the second one will be for bonus points. Okay, here we go. It says, use the definition of continuity to prove that the function is discontinuous at x is equal to 2. And with Danny, we were looking at this from before with her question that she had. This word is huge, guys. It's so important. Because that can be continuous at a point, but the whole function doesn't have to be continuous. Okay? So, rule number 1 is f of 2, if a is equal to -4. Do you see how they threw in that extra letter? Trying to confuse you? There's a lot of variables that are going to come your way. My best default rule to you is this. Guys, is this a constant? Is pi a constant? Yeah, pi is a constant, no worries. Is this a constant? Yeah, so this is about what? 2.8, nice. So on and so forth. So E is a constant. So a good rule of thumb that I show my students is just think of the alphabet. A through E can be considered constants by default. If you were not told, but you see A through E, constants. Because F usually deals with variegated functions. Go with me? Now sometimes it will say, like you have a constant K, well then K of course is a constant. But A through E is a good rule of thumb, are all constants. So what does that mean? That helps me build this piecewise function even better. Okay, so I'm looking at this and I see -4x plus 7 when x is not equal to 2, and I see 1 when x is equal to 2. The quick review of piecewise functions from both Algebra 2 and from pre-calc. Let's graph the first one. -4x plus 7, I go up to 7. I have a slope of down 4 over 1, down 4 over 1. And I have a graph that looks like this. And I'm going to graph it everywhere where x is not equal to 2. So to me, in my head, what I'm thinking of, to make a better graph, I need to be thinking of the what if moment. Go with me? So what if, let me do it in red. What if x equal 2? Well, for here, if I put 2 right here for my input, I would get -1. Do you all agree? Okay. What would I get if x equal 2 for this one? 1, because there's no variable to put anything in. So my 2 points, one is closed and one is open, will exist at 2, -1 and 2, 1. Do y'all see what I'm doing and how I'm building this with this what if moment? So at 2, 1, I'm going to be existing. And at to -1, I'm going to be open because of the domains that I see here. Okay, now let's keep going. Negative 4x plus 7 tells me that this is what the graph is going to look like. Go with me? You see how I built that? And then the other one, it's just that red dot all sitting all by itself because it's just at x is equal to 2. There's no interval here. It's just one point. Does that make sense? Okay. So you tell me, from the picture, is it continuous? No. It is not continuous. Okay, let me rephrase that. Is it continuous anywhere?
Yes.
Yes. Is it continuous at 2? No, it's not. So that's just the grunt work that you're going to do the, oh my gosh, we have to write all this out work here in just a bit. So these are like your side notes, your little, you know what I mean? Just little quick notes to get the answer, but now you still have to prove the answer. Okay? Rule number 1. F of what?
F2.
F of 2 is defined. Can someone tell me what f of 2 equals? 1. Okay? I'm trying to help you with as much context clues that I can for your next question that's going to be a little bit backwards. Unintended. Number 2. Does the limit on f of x, remember this piecewise function, exist when I approach 2? Yes. It exists. The limit does, right? Okay? Because it can be at an open dot. It doesn't have to exist as a point. So number 3, does f of 2, and you have to write it just like the rule, does the limit on f of x, rule 2, does it equal rule 1? And please don't put f of c. If you put f of c, it's going to be wrong. All the things that need to be numbers need to be numbers. All the things that need to be f of x. Let's say that I gave this to you as g of x. I'm not even kidding. One year I gave this as a quiz. And on all the piecewise functions, I put g of x. And some people, they were just used to doing one way. They wrote f of x everywhere. And they got all of those pieces wrong. Okay? So please be careful. Attention to detail is about to go up a lot. Okay? Rule 3, true or false? False, right? So you'll say, because rule 3 failed, therefore theorem doesn't hold, therefore f of x is not continuous at x equals 2. Questions? Okay, so watch. This would be 1 point, 2 points, 3, 4, 5, 6, after the therefore 7, and there's actually 2 more parts that I did not do yet that I wanted to show you specifically right here, that if you don't do them, you're going to miss these points too. The annoying part of this is all the proof part. This right here, for it to exist, what must I show that was very similar to your bonus question on that first test? Both-sidedness. I have to show both-sidedness. So I'll say the limit of f of x as x approaches 2 from the right is equal to something. The limit of f of x as x approaches 2 from the left is equal to something. Guys, can you tell me which one of these 2 piecewise functions do I use for both of these? The first one. So now I'm just going to put 2 in, right, for both of them, and what do I get? Negative 1. And because those equal, the general limit exists. So So they would be 2 more pieces for my total.
For total for what?
This is my proof to show
Okay, so you do have to show
that the
that
function is discontinuous.
Gotcha. So that's how you prove that rule too.
All of the points that I have highlighted are part of a problem. Okay? On the next one that you're going to see here in just a bit, there's an answer, but it's like 1 out of 13 points or something like that. Okay? So it's not all about the answer, it's about justification and proofs. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different pieces to this one. Questions? Alright, so now it's your turn. I want you to put your brains together, everything that we just learned from this, and in groups, I want you to use the definition of continuity to find k so that f of x will be continuous at x is equal to 2. There's a lot of pieces up for grabs, okay? Bonus, go for it. Okay, so guys, the 4 parts of calculus that you're learning and also going to demonstrate that you've learned calculus with, verbal is a huge piece that is this unit. You notice we're not doing much of algebra. We're not really doing all that many tables. We are doing graphs, but it's a huge verbal piece. To me, this is the most important one out of all the 4, because if you can do these 3, I'm sorry, if you could do V, you could do the other 3 very, very easily. Okay? So let's go ahead and look at what the answer should be. We're trying to find a k that would make this continuous. Okay? So let's go to our answer right here. Let me scroll down and show you. This is what you should have had. Let me talk you through this problem, okay? What's in the red box is what you were given. And to me, each circle is 10 points, but also I'm going to go through this in the order of progression that I think you should. I would look at these 2 things here. So I'm going to highlight it but unhighlight it because I'm not giving you points for that. But that will tell me what my what if moment is, which is right there. Okay? And if I plug in 2 in the first one, I get 2, 5. If I plug 2 in the second one, I get 2k plus 6. Okay? We know for it to be continuous, those y values, these y values right here and here have to be equal, and therefore would give us k is equal to -1/2. Okay, so from all that, all I care is, did you follow the what if moment in order to get this? Okay, so now that I have k, I went over here and I plugged k in where it was supposed to go, so that I could see what do the graphs look like. Okay, so the graphs should show this. So x's that were greater than 2, well, I'll highlight it as far as that red graph over there was this one, and that black graph over there was this one right here. Notice how the black graph was closed, but the red one was open. But they linked together at one closed point. You with me? They didn't fail the vertical line test by double dipping per se. Okay, so with that being said, that gets me to, I set my what if moment. I think I am going to set this as a point. If you set those equal to each other anywhere, I was looking for that. You got k, you got your graph, and the way you would, by proof, start this one is working backwards. You would have actually started here and said this must be true. Because remember, we're trying to make it continuous. So if it must be true, then rule 2 must exist. That means that the limit must exist as x is approaching 2. That means you would have had to have done both one-sided limits, and if you're approaching from less than 2, you would get 5. If you're approaching greater than 2, or from the right of 2, you would get this 2k plus 6. And therefore, at the very, very end, you're going to say f of 2 is defined. F of 2 is 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? How many of those did y'all get?
Perfect.
9? Okay, so 180. I think I gave one more this time, and I'm okay with that. Y'all got 180 as well?
You just asked us. You just put us.
Oh, my bad. Y'all got 180? Okay, cool. And 180. Okay, this last one is the most difficult one. I don't think it's that difficult, but it's because I've seen it a lot. For you, the first time you see it, it looks difficult, but it's not really, okay? So let's go ahead and work this one together. All right, so let's go back to our notes. And it's this one right here. So next time we're going to do intermediate value theorem. But we're going to do this. Use the definition of continuity to find an A and B so that F will be continuous everywhere. So together, we're trying to find what are these two variables right here and here that would make this continuous everywhere. There's a lot of points. First, let's start off with what if. What if x equaled what, do you think?
3.
Negative 3. That's one of them. And then what if x equaled what? 1. So guess what? We're about to do basically two problems. Okay? So here we go. If x is equal to 3, that means we're going to use this and this function right here. And we're going to plug in a negative 3 where we find x. You with me? So there are 2 points that we're going to find are negative 3, negative 17. What's the other one? Negative 3a plus b. Nice. Okay? Let's do our other what if moment with x is equal to 1. This time we're looking at, because x is equal to 1, we're looking at these two. So the first point that we'll have is 1 a plus b. Nice. And then what's the other one? 1, 3. And our goal to make this continuous everywhere is that this has to equal that, and this has to equal that. Do you all agree? Okay, here we go. So, negative 3a plus b is equal to negative 17, and 3 is equal to a plus b. What do you think I do from here to solve for a and b? Substitution, or you could do elimination. Either way, right? This is what we learned in systems of equations for Algebra 2, right? Which one do y'all want to do, guys? It doesn't matter. Let's do substitution. Let's say that a is 3 minus b. So 3 minus b is going to be substituted over here where a was on this equation. And now we're going to solve for b. Okay? Say again?
My bad.
Okay. So we'll get a negative 9 plus 3b plus b is negative 17. So we get 4b is equal to what? Negative 8? So b, negative 2. So if b is negative 2, what's a? 5. And now you've just done all your grunt work to know what values am I looking for. So this is, again, very small percentage of the entire question is the answer. Are we good? But we at least know what we're looking for. Yeah.
So what if we use a different method to find A and B?
That's okay.
Okay.
Yeah, you could do elimination. You could do whatever you want. You could do reduced echelon form if you want. You know what I mean? Remember that? The Gaussian elimination? Anyway, no one's going to do that. Please don't do that. Okay. Let's do x is equal to negative 3. We're going to do the whole proof for this side first, and then we'll do the whole proof for that side. Are there any questions, though? Okay. So here we go. These will be or must, well, 9 out of 10 times start from where? No, 10 out of 10 times will always start from which of the 3 rules? Rule 3. Rule 3. Okay? So here we go. We're going to say, Rule 3 is, you tell me, what do I write here, guys?
You say
F of that.
f
or
of
f
negative 3.
The limit of f of x negative 3 is equal to
F of negative 3.
f of negative 3. Okay? And then when we come back, we know that f of negative 3 is defined. Is f of negative 3 defined?
Yes.
Yep. What is it?
Negative 17.
Negative 17. So we're going to put f of negative 3 equals negative 17. Here comes the second part. We need to show that the limit exists. And we're saying that it must exist. So we're going to say the limit of f of x must exist as it approaches negative 3. And yes, you guessed it. That means we're going to break this up now into two separate parts. And we're going to have to show that work. B was what again? Negative 2?
Negative 2.
Okay. So B is negative 2. Alright, so breaking it up, the limit of f of x as x approaches negative 3 from the left. Okay, here we go. Which of the domains, 1, 2, or 3, am I going to use for that? Which one?
1.
1, right? Because I'm approaching negative 3 from the left. So that means it's less than negative 3. So this is negative 17. The limit of f of x as x approaches negative 3 from the right, which one am I using? The other one, right? And what am I going to put here?
5b minus, or 5x minus 2. Would you not plug in the,
It'll be negative 3a plus b.
oh, would you not plug in the a and b values?
Oh, I see what you're saying. You went all the way. So here's what I'll say. Please do it like this, and then plug in the a and b values thereafter and set them equal to each other just to verify. But this is how I want it built. Because now you've started with Rule 3, you've gone back, you've established this must, you've established the work, and right here, guys, what we did, we need to set these equal to each other for this general limit to exist. And we did that, where did we do that? We did that way up here. You with me? We did that way earlier on. But it's easier to see in the what if moment than in the proof moment. The proof, I'm looking at way too much stuff. And it's easy to get lost. You with me? So on this one, I know we only did half and we really only had time to do half. The other one would be the same. Only you would be plugging it in with that what if moment of x is equal to 1. Watch how many points you would get. 1, 2, 3, 4, 5, showing that these were equal to each other and that you were solving is 6, 7, and the other one you would have 7 more, and then the answer itself 14, 15, 16. So that would be a 320 point question. Okay? Just for FYI. Alright guys, go ahead and start putting up.